Alright, silly people, here's the situation. Griffiths is asking us if we take uh, just a polynomial that has every order of x up to x to the n minus 1 with constants attached to them, does that form a vector space? Um, and yeah, it does. And so we can run it through the usual battery of tests, right? Um, One, does the zero vector exist in this space? Yeah, you can just set all of the constants a equal to 0, and then you get that the whole thing is the null vector. So past that check. Is it closed under vector addition? So if we just take our original vector here, xn minus 2 plus dot 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 a2 x squared plus a1 x plus a0, and we got another vector to it where all of the constants are b's instead of a's. Dot 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 b2 x squared plus b1 x plus b naught, where b is some complex number. Guess what? You just get a n minus 1 plus b n minus 1 um, times xn minus 1 plus an minus 2 plus bn minus 2 times xn minus 2 plus dot 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 a2 plus b2 x squared plus a1 plus b1 x plus a naught plus b naught. All of those combinations, ai plus bi, is still a complex number, so therefore it's closed under vector addition. The last thing to check is if it is closed under scalar multiplication, so we can multiply um, the whole thing by another complex number c plus a naught, where c is a complex number. And then all of these constants get multiplied by c, ca2 x squared plus ca1 x plus ca naught. And then any complex number times another complex number is just another complex number. So cai is a complex number. Therefore, it passes the check of being closed under scalar multiplication. So it is, in fact, a vector space. So that's the entire vector space. It has dimension n because it has all of those n minus 1 x terms, but also the constant. So that'll give you another one. So it's just n dimensions. Then the problem asks, what if you constrain it to only the even polynomials? Is that still a vector space? Yeah, it is. So all polynomials even. Um, so that'll look like A2, or it's actually going to be A naught plus A2 x squared plus A, or plus dot dot dot, I'll say, dot 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 plus A n minus 2 x to the n minus 2. That's what it will look like if n is even, right? Because n minus 2 will still be even in that case. If n is odd, it'll look something different. It'll end with the term a n minus 1 to the x minus 1 if n is odd. And so you kind of get different sized dimensions depending on whether or not the thing is even or odd, right? Because you miss a term if you don't, if n is even. So this isn't n over 2, this is n over 2 minus 1. And this one is actually just n over 2, right? Uh, those are the dimensions of the vector spaces. Um, then Griffiths asks, uh, like, what if you set the leading order constant to 1, what would happen? Well, then it's not a vector space anymore, right? It fails the first test. So if an minus 1 equals 1, then you can try to make the null vector, but it's not going to work. You just set every constant except for the leading order 1 to 0, but that's not the null vector, so it's not a vector space. Then he's like, what if you use every polynomial that has the solution of 0 at x equals 1. So if polynomials equal 0 at x equals 1, then all you do is you take every polynomial term that was in the vector space and turn it into x minus 1 to the I, and it's still a vector space. And it has dimension n, same as the one up top. Wrong. So it turns out you can't have the constant term at the end unless that is 0, because it's the only one that satisfies it being 0 at x equals 1. So it actually has n minus 1 dimensions. The clever thing about this is that the next one that he wants us to check is not so nice. So he wants us now to do every polynomial that equals 1 at x equals 0. And you'd think that you would just do the same isomorph. Change every x to the I to x plus 1 to the I. But this actually fails because you can't make a null vector with this. Because if you set all of the constants to 0, like you would have before, plus 0, x plus 1 to the n minus 2 plus dot 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 plus x plus 1 squared times 0 plus 0 times x plus 1 plus 0. Well, everywhere you just get a bunch of polynomials where the solution equals 0 for every one of these. So you get the null vector true by setting all of the things set to 0, but like now you're out of the vector space, since now all the polynomials equal 0 always. So not a vector space. All right.